You have some data for which you create a bar chart. Think for instance of grades or measurements of something in the real world. You see, it's a Gaussian that kind of fits the data really well. You need to find the parameters of the Gaussian. They are unknown. Of course you can use a maximum likelihood estimate, but you see there are outliers. So is there a robuster estimate, or can we encode prior knowledge? And we can. In this video we will derive the posterior and the map for the univariate normal with unknown mean and unknown precision. Hi, welcome to this new video. The agenda for this video is that we will first figure out the conjugate prior for the particular problem. Once we found this prior, which turns out to be the normal gamma distribution, we will look at a visualization of it to get an intuition about it. With the help of this prior, we can derive the posterior, and with the posterior, we can derive a maximum-A-Posteriori estimate. In the end, we will look at TensorFlow probability in order to better understand what we derived with the help of a problem. As said in the intro, we have the problem of parameter inference based on the data. And the problem is that our data is noisy or it is some sort of corrupt. So if we use a maximum likelihood estimate, this leads to wrong solutions or leads to overfitted solutions. So we need to encode prior knowledge or also regularization in order to get a more robust estimate. And we did something like this before. In two prior videos, I derived the posterior and the map for either the mean being unknown and the variance or precision being known, and the other way around. But in this video, we will derive a general result that is valid if both are unknown and if you want to encode prior knowledge for both of them. So let us note this down. We want to regularize both of these, both of the parameters. So this means we want to regularize the mu, the mean, and the sigma, sigma squared, or tau. These are all the same, defining the spread of our distribution. And in order to do so, we need a prior that is valid for both of these parameters at the same time. So we need a prior over mu and tau, and I will work in terms of the precisions again because it just makes our life a little bit more easy. But once you have found the result, you can easily rearrange it in terms of the other quantities. And the problem here is that we need a multivariate prior. So we need something that is defined over these two random variables jointly. And in order to figure out what kind of a prior we need, let us look at the likelihood of the Gaussian. The likelihood was the quantity we also used in the maximum likelihood estimate, and it is defined as an L over D given mu and tau, where we just take the product over all our entries in a dataset. So we have the product from I0 to capital N-1 over the normal of the xi observation under mu and tau inverse in order to mimic the variance here. And recall, a dataset is what we basically also use to create our bar chart from. So these are observations. Plugging this into the functional form of the normal distribution, we get the product from I0 to capital N-1 over the square root of tau over 2 pi times the exponential of minus tau over 2 times xi minus mu in brackets squared. Then let's simplify this. If we apply the product to this term n times, so it's a constant in a sense, it does not contain any I for the product, then we have to raise this to the power of n. So we get tau raised to the power of n over 2, because tau is under the square root, so it's raised to the 1/2, and we multiply it n times with itself, so it's n over 2, and we divide it by 2 pi also raised to the n over 2. And then we have the exponential, and if we multiply the exponential n times with its corresponding xi, then this actually turns out that we have a summation here, because we are summing up all the exponents of the different factors, which leads to the summation in the exponent. So we have minus tau over 2, which would be the multiplicative constant here, and then we have the summation from I0 to capital N-1 over xi minus mu in brackets squared. And what we have here is called the sum of the squared differences from the mean, so sum of squared differences from the mean, and we can simplify this in order to move the mu outside of the term that is including a summation. And I derived a general result for this in a video that you can check out, but you can also just trust me that this is a way to express this. And I will also work in terms of the proportional, because this 2 pi raised to the n over 2 does not greatly affect the way we should choose a prior, right? So we can just ignore it and work in terms of the proportional. And then we have tau raised to the n over 2 times the exponential of minus tau over 2 times, and then let's apply the formula, and here we get an opening bracket, and we have the summation from I0 to capital N minus 1 over xi minus x bar plus n times in brackets x bar minus mu in brackets squared, then closing brackets for this and closing brackets for the exponential. And I introduced the x bar in here, and x bar essentially is the mean or the average of our data points. In essence, it is just the maximum likelihood estimate. For the next step, let us multiply the tau over 2 with each of the two components in here. And I will also use this tau to the n over 2 by splitting out the exponent in having an n minus 1 over 2 and a tau raised to the 1/2. So we are getting tau to the n minus 1 over 2 times the exponential, and then I will first have the minus 1/2 summation from I0 to capital N minus 1 over xi minus x bar, and then closing brackets times tau. So I just multiplied this one with the first term here, and I moved tau to the right side of it. And then I multiply with tau raised to the 1/2. And if I would multiply these two, so then the exponents would add together, and then I'm back at tau to the n/2. And then the last term is this one here, which is the exponential of minus tau times n over 2, and then in brackets x bar minus mu squared. And then we reach the point where we can look at the functional form of this likelihood. So I will now try to investigate it and find the conjugate prior for our missing or unknown tau and mu. So we want our prior over mu and tau to be, well, tau raised to something. That's what we have here, times e to the minus something tau. And here we have the square root of tau. And here we have the exponential of minus 1/2 of something times tau times something minus mu in brackets squared. I put a lot of these somethings, like these dots in here, but I hope that you can see the idea here. So whenever we have constants that are dependent on the data set, so we have an n in here, we have an xi, we have the x bars, we just replace them with placeholders, so in a sense with constants. And here we would have one, and then here we would have one, and so on and so forth. Let us introduce some names for them. Let's call this placeholder an alpha 0, and this one a beta 0. This one I will call a tau 0, and here I will call a mu 0. And I will not just have an alpha 0 here, I will have an alpha 0 minus 1. And this might remind you of something. The first is an unnormalized gamma distribution. So that is an unnormalized gamma. And here we have an unnormalized normal distribution, but there is another factor in here. It's not just like that the tau appears in the exponential, but it's some sort of like a modified tau. So let's call this an augmented unnormalized normal, which is really just complicated for saying that we are working in terms of the proportional here. So augmented unnormalized normal. And this particular distribution that is given here is called a Gauss-Gamma or a normal gamma distribution. So we have an Gauss-Gamma or normal gamma distribution. And the tau 0, the mu 0, the alpha 0, and the beta 0 are the hyperparameters. They are the parameters of this prior. So we have our prior over mu and tau as the normal gamma over mu and tau with the hyperparameters alpha 0, beta 0, mu 0, and tau 0. And the functional form is what I just wrote down. So we have the tau raised to the alpha 0 minus 1, then e to the minus beta 0 tau, or let me put some space in here so that I can add the normalization. And then we have the square root of tau times the exponential of minus 1 over 2. And here we have the tau 0 times tau, and then multiply it with mu 0 minus mu in brackets squared, closing brackets for the exponential. And then let's add the normalization in here. And first, let us add the normalization of the gamma distribution, which is beta 0 raised to the alpha 0 divided by the gamma function of alpha 0. And we have to add the normalization for our exponential function. And it turns out that we have to divide by 2 pi. And since we also have an changed precision in here, we also have to multiply with it in this normalization constant. So we have a tau 0 times tau also under the square root here. Since we have to look at a new distribution for this prior, I want to give you some visual insights on how this distribution looks like. So here we have the functional form again that I just introduced. And then we have 4 sliders for the hyperparameters of this distribution. And on the right side, we have contour lines for the probability density at each spot in this 2-dimensional plane here. On the x-axis, we have tau, which is the precisions. So its values have to be strictly positive. So we go from 0 to 5. And then we have the mu, which can take any real valued value, and it is from -5 to +5 here. And we see that we have a peak of our distribution, so there is a maximum of it, which is around here, with a tau value of 1.5 and a mu of 1. And then we have these contour lines, and they have a particular shape. You can almost call them some sort of like triangular, and the edges of the triangle are sort of like inclined inwards towards the center. And we can play around with this distribution. Of course, if I change the mu value, then I don't change the shape, I just move the distribution more towards this mu value, or actually I put it on this mu value because I have it at -4, and then you see the peak is also approximately at -4. But I can also play around with the other values. So we have the tau 0, and I think of the tau 0 as some sort of precision multiplier. This means that if I change it to a lower value, then it is also augmenting the probability density to be more towards the left, right? So because I have this multiplier which tells me that I have a lower precision, so I also encode this as lower precision. And what you can also see here, there is no more clear yellow color because the distribution of the probability mass is now spread out over a wider region than we had it when we have a higher tau 0 value, for instance. If we go up to 2.5, then it is looking like this. The tau 0 value also affects the shape of the distribution, or the shape of these contour lines, so that they are like not as wide anymore and like more narrow and really sharp distribution in this sense. And you can play around with it a little bit. You can also adjust the alpha 0 value, and you might see a similar behavior to the gamma distribution, which makes sense because this alpha 0 is really close to what the gamma is. And if I go over this point below 1, then I also see that it's kind of like melting towards this y-axis, if you could call it like this. And it's quite interesting to play around with it. It gives you a lot of freedom in order to choose your hyperparameters to encode the knowledge about your parameters. Because essentially what we do here is we model alpha, beta, mu, and tau in order to then encode our knowledge where we expect the mu and the tau of the distribution to lie. With this information in mind, we can now finally express a directed graphical model for the problem that we want to solve. So let's call this the DGM. And recall, our problem was to infer the parameters of a normal distribution because we observed values. I will call these observed values xi. So for instance, think of some grades or think of measurements, something that is normally distributed. And we have n of those. And the normal distribution depends on the 2 parameters of a mu and a tau, or standard deviation variance, whatever you want to use. And they are both latent, so they are no longer deterministic, they are latent because we want to encode prior knowledge on them. And we know that these 2 random variables take hyperparameters each. So for the mu, it is an mu 0 and an tau 0. And for the tau, it is an alpha 0 and a beta 0. And what we've also seen is that the tau also affects the distribution of the mu. Because if you go back up here, then we see that the tau that is inside of this distribution also is part of this distribution. And this makes sense because we would factor this 2-dimensional distribution in the way that we have the p of mu and tau, and we would factor it as p of tau and p of mu given tau, and then we already see that we have this relation from tau to mu. And this also means that the Gauss-Gamma or normal gamma is not a Gaussian times a gamma. Okay, let me note this down. It's not a normal or Gaussian times a gamma. And with this information on the conjugate prior, let us note down all the individual distributions here. We have tau distributed according to a gamma over tau under the hyperparameters alpha 0 and beta 0. Then we have the mu distributed according to a normal over mu under first deterministic mu 0. I will still use the vertical bar because we then have a mixture of a deterministic and probabilistic dependency with the tau 0 and the tau because they appear as the product. So we have tau 0 times tau in brackets inverse, and we do the inverse again because we mimic the variance. And I think then it also makes sense that I call tau 0 the precision multiplier here. And with tau and mu, we can then define xi to be a normal distribution over xi given mu and tau. Let us now use this directed graphical model to express the joint probability density function over all the three random variables. So let's call this the joint. And for this we want to find the probability over tau, mu, and x vector. And this factors according to first p of tau, and it does not have any dependencies because it's a root node. Then with p of mu given tau, and then with p of vector x under mu and tau. And then we know, of course, this one was our likelihood that we had before. So we can also fix the x, and let's do this. So let's fix the x to the observation d, and then also fix it here, which would also be a shorthand way of just saying that we have p of tau, mu, and d. And then we get p of tau, then p of mu given tau, and then times the product from I0 to capital N-1 over p of xi given mu and tau. Plugging in all we got, we have first for these two, we get the Gauss-Gamma, which is first the gamma normalization constant multiplied with tau raised to the alpha 0 minus 1 times e to the minus beta 0 tau, then times this one here with the normalization constant, giving us the square root of tau 0 tau over 2 pi times the exponential of minus tau 0 tau over 2 times mu minus mu 0 in brackets squared. And then we have our likelihood, which we also can take from our earlier calculations up here and just plug it in. So we have times the square root of tau over 2 pi in brackets raised to the power of n, or you could also have this separate, but let's keep it together, times the exponential of minus tau over 2 times the summation from I0 to capital N-1 over xi minus mu in brackets squared, and then closing brackets for the exponential. Now we have the joint distribution. Let us now talk about the posterior distribution. And the posterior is also what we actually want. So it's the probability over tau and mu given d. So the probability of our parameters given the observations that we made. And by Bayes' rule that we have here, where we get a long fraction with p of d given tau and mu, and this is just our likelihood, times p of tau and mu, which was our prior, the normal gamma, divided by p of d, which is the marginal of our dataset. And we don't want to calculate the marginal, so we work in terms of the proportional and say p of d given tau and mu times p of tau and mu. And this is nothing else than the joint distribution. So let's write this down. This is p of tau, mu, and d that we have here. And with this, we again figure out that the posterior is proportional to the joint. So we can just work with the joint that we derived and make our simplifications, modifications in order to then arrive at another functional form. And recall, we expect the normal gamma to be the conjugate prior. So in the long term, we want to arrive at something that looks like the normal gamma again. Okay, so let's plug this in. And we have the posterior of tau and mu given d is proportional to. And for this, I will ignore all the normalization constants here. So this one, I will ignore the division by 2 pi. And I will also ignore the tau 0 here. And this is because it is also just a multiplicative constant in a sense. It also appears in our exponent, so we can safely ignore it because we still have it within our functional form. And here we also have the 2 pi, so I will also ignore this. And then we get the following. So first, we have the tau raised to the alpha 0 minus 1 times e to the minus beta 0 tau times tau to the 1/2, this is the square root of tau, times the exponential of minus tau 0 tau over 2 times mu minus mu 0 in brackets squared, closing brackets for the exponential, times tau over n/2 times the exponential of minus tau over 2 times the summation from I0 to capital N minus 1 over xi minus mu, and then closing brackets, and another closing brackets for our exponential. And let us look at the functional forms that we have here. So we have three components where tau is in the base of an exponential, and then we have another three where tau is in the exponent. So here, here, and here. So let's merge them together in some senses. So we get this is equal, and by equal I mean it's equal to this form. It is still proportional to the posterior. So we have tau to the alpha 0, and I will add the n over 2 here to then have this form again, and then I will keep the e to the minus beta tau, I will keep it separate, I won't put it together with the others. I will keep the tau to the 1/2 also separate, because this is kind of looking into the future. In the long run we then want to find the Gauss-Gamma again, and there we then also have the square root of tau again, so we should also keep it separate here, but it does not greatly matter. You can also like add the exponent here and then later on recover it, but it's probably helpful if we keep it like this. And then we have the two long exponents here. Let's add them together. So we have the exponential of minus tau 0 tau over 2 times mu minus mu 0 in brackets squared, and then minus tau over 2 times the summation from I0 to capital N minus 1 over xi minus mu in brackets squared and then closing brackets for this exponential. And in the exponential, we see that both of the components contain tau over 2, so we can factor it out. So we keep the tau to the alpha 0 plus n over 2 minus 1 times e to the minus beta 0 tau, then tau to the 1/2, and then the exponential of minus. I will also factor out the minus, and then we have here a tau 0 times mu minus mu 0 in brackets squared, plus the summation from I0 to capital N minus 1 over xi minus mu in brackets squared, then closing brackets and another closing brackets for the exponential. And in order to find the functional form, we have to simplify this exponent. So we have to create two components essentially, one that is only in mu and one that is only in xi or terms that are not mu, also the other constants, hyperparameters that appear here. So let's try to find some modifications of this term. I will call this xi for the time being in order to define this. So we have xi is tau 0 times mu minus mu 0 in brackets squared, plus the summation from I0 to capital N minus 1 over xi minus mu in brackets squared. And here we can again apply the simplification of squared distances from the mean. So that yields first the tau 0 and this term here. Then we have plus the summation from I0 to capital N minus 1 over xi minus x bar in brackets squared plus n times x bar minus mu in brackets squared. And recall x bar was our empirical mean or our maximum likelihood estimate of the mean. And then we are getting closer to where we want to be. But here we have two quadratic forms for the mu, right? So it is here and it is here. But in order to finish and to find a posterior, we have to have only one quadratic form in mu. So let us apply the rules for the sum of two quadratic forms. So sum of two quadratic forms. And for this, we have to identify the parameters. And we have an a here. We have a y here. This will be our b. And of course, we can always change the order here in these quadratic forms. That does not greatly matter. So let's let this be our set. So let us note this down. We have an a of tau 0. We have a y that is mu 0. We have a b that is n. And we have a set that is x bar. And then we derived the sum of two quadratic forms in another video, for which we have an c being a plus b, which in our case would be tau 0 plus n. Then we have a d, which is given as ay plus b set over a plus b. Then plugging what we have, so a times y would be tau 0 y 0 plus b times z is n times x bar, and then we divide by a plus b, so it's tau 0 plus n. And we have an e that is given as an a times b times z minus y, or y minus z, in brackets squared over a plus b. So we have a times b, it is tau 0 n, and zy would be mu 0 minus x bar in brackets squared over a plus b, which is tau 0 plus n. And this allows us to rearrange our xi into an c times mu minus d in brackets squared plus e, and then with the term who wasn't involved in this, so this one here, the summation, plus the summation from I0 to capital N minus 1 over xi minus x bar in brackets squared. And then let's plug in what we have for this. So we have xi will be our tau 0 plus n in brackets times mu minus this one, so tau 0 mu 0 plus n times x bar over tau 0 plus n, closing brackets, and then squared, plus dE, which will be tau 0 n times mu 0 minus x bar, closing brackets, squared over tau 0 plus n. And then plus the term with the summation, so plus the summation from I0 to capital N minus 1 over xi minus x bar in brackets squared. And then we have our xi fully simplified, because we then have one term which is quadratic in mu, and all the other terms do not contain mu at all. So we can plug this back into our proportional posterior. So we had the probability over tau and mu given a dataset was proportional to tau raised to the alpha 0 plus n over 2 minus 1 times e to the minus beta 0 tau times tau to the 1/2 times the exponential of minus tau over 2, and then we had the xi here. Then let's plug in the xi and let us multiply the minus tau over 2 with each of these components individually. So we get, first we keep the tau raised to the alpha 0 plus n over 2 minus 1 times e to the minus beta 0 tau times tau to the 1/2, and then times the first exponential term, which will be this one here, and we have minus tau over 2 times tau 0 plus n times mu minus tau 0 mu 0 plus n x bar over tau 0 plus n in brackets squared, and then closing brackets for this exponential. Then there's the next exponential, which is minus tau over 2 times this term here, so tau 0 n times mu 0 minus x bar in brackets squared over the tau 0 plus n, and then closing brackets multiplied with another exponential, which will be minus tau over 2 times the term with the summation, and then we have this one here, which is xi minus x bar in brackets squared, and then closing brackets for this exponential. And recall, we now have 3 exponentials, one where mu is in it, and 2 where it isn't in it. And for this we will do as follows. Because we want our exponential that is containing the mu to be part of the subsequent normal of our normal gamma distribution, so we put all the terms that do not contain mu inside of this term with e to the minus beta 0 tau. So let's do this. I will note this in yellow. So we have first our tau raised to the alpha 0 plus n over 2 minus 1. And then multiplied with the exponential, and then we have a minus, opening brackets, first a beta 0 plus. Since I want to factor out the tau, I will ignore the tau, and we also have the minus factor out, so we have 1/2 tau 0 n, then the fraction of mu 0 minus x bar in brackets squared over tau 0 plus n, and then plus 1/2 times the summation from I0 to capital N minus 1 over xi minus x bar in brackets squared, and then closing brackets for the multiplication and closing brackets for the exponential. And of course we have to squeeze in a tau here, because that's the common factor in all of these. And then we have the tau raised to the 1/2 times the exponential of minus tau over 2 times tau 0 plus n, and in brackets mu minus tau 0 mu 0 plus nx bar over tau 0 plus n, and then closing brackets squared for this term here, and then closing brackets for the exponential. With this, we are already at a finish line. It might not look like this right now, but let me go back up to the Gauss-Gamma distribution that we introduced. Here we had the following terms. Ignore the normalization for a moment, but here we have the alpha parameter, the beta parameter, we have the tau 0 parameter, and we have the mu 0 parameter. Now let's try to find the alpha n, beta n, tau n, and mu n, or the parameters of our posterior, in this mess here. And first we see that must be our alpha n. And this lengthy term here must be our beta n. Then this must consequentially be our tau n, and that is our mu n. Let us also note this down, that it is just another Gauss or normal gamma distribution here. And you noticed I used these names kind of interchangeably. Okay, let us note all these parameters down individually. So we have an alpha n, which is an alpha 0 plus n over 2. That's our first result. Then we have a beta n, and then let's write this down. So we have, this is beta 0 plus 1/2, and then we get tau 0 n times this one here, which will be mu 0 minus x bar in brackets squared over tau 0 plus n. And here we have the term with the summation plus 1/2 times the summation from I0 to capital N minus 1 over the square differences from the mean. And then we have this one. With this we found our next result. Then let's go on to the other parameters. We have a tau n according to tau 0 plus n, which you can see here, which is the third result. And the last result is mu n, which is then given as this term here. So it is then tau 0 mu 0 plus, and then we have n times x bar over, and then the term tau 0 plus n. And then we have our normal gamma of the posterior fully defined. Then let's find the posterior accordingly. So we have the p of mu and tau given a data set is another normal gamma distribution over mu and tau under the parameters alpha n, beta n, mu n, and tau n, with what we just defined here. And then let us also note this down for completion, that we have first, or the functional form of the normal gamma with, or the posterior normal gamma, which is the beta n raised to the alpha n over the gamma of an alpha n times tau raised to the alpha n minus 1 times e to the minus beta n tau times the square root of tau times tau n. And we have to also insert this tau n here again in order to normalize our distribution, divided by 2 pi times the exponential of minus tau 0 over 2 times mu minus mu n in brackets squared, and then closing brackets for the exponential. And that is the distribution that defines our posterior over mu and tau. The posterior is of course extremely helpful, as it provides us with a full probability density distribution over the parameters, but often we are just interested in a point estimate, or in essence in a formula that we can evaluate in order to infer a parameter with our prior knowledge. So now let's look at the Maximum-A-Posteriori estimate, and for this we will find the mode of the Gauss-Gamma distribution. So it is the mode of the Gauss-Gamma or normal gamma. For this we have to maximize it, and we can define this as following, that mu map and tau map will be the arc maximum over all possible mu's and all possible taus that are greater than 0. Even though that this is a constraint, it is not really relevant for us because the maximum that we will be finding is adhering to this property over the posterior, which is given as p of mu and tau under the data. And you might have seen that I interchangeably used mu and tau here. It does not greatly matter which one is first and which one is second. Similar to derivations for the likelihood, it is easier to work in terms of the log space. So let us define the log posterior. In other words, this would be log p of mu tau given d. And this log posterior is given up to an additive constant because we will ignore the normalization. So first this one kicks out, and then we apply the logarithm to this one here, and it brings down the exponent in front of it, and then times logarithm of tau. So we have alpha n minus 1 times the logarithm of tau minus, and then we have, well, e to the minus beta tau, so we get like the minus that I already have here, so minus beta n tau, then plus, and here we have the square root, and we only consider the tau. I will kick out all the terms that are parameters or constants. So we have tau to the 1/2, and if we apply the logarithm to it, then we get 1/2 times logarithm of tau, so plus 1/2 times the logarithm of tau. And then lastly, we apply the logarithm to the exponent, so both cancel, and we have a minus tau 0 over 2 multiplied with mu minus mu n in brackets squared. Oh, of course, and this shouldn't be 0, should be a tau n. Then let's first maximize with respect to mu n. So let's take the partial derivative of our log posterior with respect to mu, and then we see this cancel, there's no mu, there's no mu, there's no mu, there's a mu, so we get minus tau times tau n times 2 in brackets mu minus mu n, and there's no inner derivative, and this has to be equal to 0. And then we see, well, we can cancel all of this out, and we are left with mu minus mu n is 0. And then we obviously see that the maximum a posteriori estimate is the mu n, which is the parameter of our posterior normal gamma distribution. Then let's take the partial derivative of the log posterior with respect to the tau parameter. So we derive log p with respect to tau. This will be a little more effort. So first we get alpha n minus 1 over tau. So alpha n minus 1 over tau. And then here we just get minus beta n. And here the derivative will be 1 over 2 tau. So plus 1 over 2 tau. And here we take the derivative, and then the tau cancels, and we're just left with everything else here. So we have minus 1/2 mu minus mu n, and this has to hold to 0. And we can already plug in the maximum a posteriori estimate that we found here, and then we see this is mu n minus mu n, so this cancels, and then all the term cancels here, and we are only left with what we have here. And for this, let's multiply with tau in order to get it out of the denominator, and then we have alpha n minus 1 minus beta n tau plus 1/2 is 0. Well, minus 1 plus 1/2 will be minus 1/2, so we have alpha n minus 1/2 minus beta n tau. Then let's bring the beta n tau on the other side and divide by beta n. So this can be equivalently written as tau is alpha n minus 1/2 over beta n. And with this, we found the maximum a posteriori estimate for the precision tau. But of course, both the estimates are still in terms of the general parameters of our normal gamma distribution. I mean, in essence, we just found the general mode of a Gauss-Gamma distribution or a normal gamma distribution. So let's plug in the values. I will call this with values plugged in. And then we first have to plug them in here. And we get that mu map is tau 0 mu 0 plus n times x bar over tau 0 plus n, and that's our first finding. And of course, recall that the x bar is our maximum likelihood estimate. And I think that's also quite cool to see here what the maximum a posteriori estimate is kind of representing. And it's just a linear combination, or you could also call it a weighted average of the maximum likelihood estimate and our prior assumption. So it's a linear combination. That's cool, right? I mean, that's how our prior knowledge is encoded in the maximum a posteriori estimate. And for the precision, we would get our tau map according to alpha 0 plus n minus 1 over 2 divided by, and then we have first beta 0 plus 1/2 n times tau 0 times then the fraction of mu 0 minus x bar in brackets squared over tau 0 plus n plus 1/2 times the summation from I0 to capital N minus 1 over the xi minus x bar in brackets squared. And that's the result for our tau map. I think it's probably easier to discuss this in terms of the maximum a posteriori estimate for the standard deviation, and recall that the tau was defined as 1 over sigma squared. So in order to get the map for the standard deviation, we just change the fraction here and take the square root of it. So for completion, let's note this down. The maximum a posteriori estimate for the standard deviation will then just be beta 0 plus 1/2 n times tau 0 times mu 0 minus x bar in brackets squared over tau 0 plus n plus 1/2 times the summation from I0 to n minus 1 over xi minus x bar in brackets squared. And then we divide by the term that was in the numerator before, so an alpha 0 plus an n minus 1 over 2. Of course, we have to take the square root of it. And what I find cool is that here you essentially see n times the maximum likelihood estimate for the variance. So this one here is equal to n times sigma MLE squared. And then you see that actually our map estimate is based on the prior knowledge beta 0 plus our maximum likelihood estimate plus an effect based on the maximum likelihood estimate of our mean, because that was the mu MLE. And I would encourage you to look at this for a little bit, and it's quite impressive, to be fair, how we derived this based on the ideas of our conjugate prior, and we have now encoded a regularization into our estimator, which will be extremely helpful for noisy and corrupt datasets. Lastly, let us look at an example in TensorFlow probability. For this, we have to first generate some data, because we want to work with artificial data. So we have to define a true mu and a true sigma. I will, for instance, center our true normal distribution around 5.0, and it will have a standard deviation of 2.0. And of course, this means it has a variance of 4 and a precision of 1 over 4 or 0.25. So I will also note down our tau true to be 1 divided by sigma true raised to the power of 2, and then we see that this is 0.25. Then let's create the random variable, and I will just call it x, because it is a general random variable. It can be many things, for instance, measurements that you conduct, or grades after an exam, anything that could potentially be modeled by a Gaussian. So we will use TensorFlow probability.distributions.normal, and we center it at our mu true, and we use a standard deviation according to our sigma true. Then we can create a dataset based on it by sampling our random variable, for instance, 100 times. And this also defines our n to be 100. I will just use a floating point number here for later convenience. Then let's look at a dataset, and we see these are measurements, and we see there are around 5, and we have some really off measurements, and so on and so forth. Then we can first infer a maximum likelihood estimate according to the derivation we did in an earlier video. So I will use mu MLE, and the maximum likelihood estimate is nothing else than the mean. So I will use reduce mean on the dataset, and then we can look at it, and we have a mu MLE of 4.78. So it's getting quite close to our 5.0, but it's a little bit off. Probably our dataset was not as representative for the underlying distribution. Then the sigma MLE was defined as the square root of the mean distance from the mean. That's a little mouthful, but in essence, it is just the square root of the reduced mean of our dataset minus the MLE mu that we just found in brackets raised to the power of 2. And then we can look at the MLE, and we see it's 2.01. That's quite a good estimate, because 2 was our true solution. Now we want to define the Maximum-A-Posteriori estimate. For this, we have to first encode our prior knowledge. So let's start with a mu 0. In essence, this is where we would expect our mu to be. And for instance, maybe we wouldn't think it's 5.0, so we think it's 4.9. Then we have to define a tau 0, which is a precision multiplier in essence. And here let us also select something that is close to our true tau. So recall the true tau was 0.25. So for instance, let us do 0.24. Then we have to define an alpha 0 and a beta 0. And I will use maybe an alpha 0 of 5.0 and a beta 0 of 4.0. Of course, this is something that you could easily model by looking at the interactive chart and then selecting those hyperparameters that best encode your prior knowledge. Then based on this, let us define the map estimate, and for it I will bring over our derivations that we did before, and let us start with the Maximum-A-Posteriori estimate for the mu. And for this we have first our tau 0 multiplied with the mu 0 plus the n times and x bar. X bar was essentially our mu MLE. Then we divide by the tau 0 and we add an n. And then we can look at the map estimate and we see it's 4.77. So it's also quite close to our 5.0. We will discuss it shortly. We don't want to do the tau, we want to go for the sigma straight. And so we do sigma map for the standard deviation. And for it we have to take the square root of, first we have the denominator, which is beta 0 plus 0.5 times n times tau 0 times, and then we have mu 0 minus mu MLE in brackets raised to the power of 2, and then we divide by the tau 0 plus n. If you got lost, I'm here right now. And then we have a plus 0.5. And here we have the sum of squared distances from the mean. And in essence, as we've seen here, this is nothing else than n times sigma MLE squared. So n times sigma MLE squared. Then we close the brackets for the numerator. And in the denominator, we get an alpha 0 plus an n minus 1. So an n minus 1 divided by 2. Then close and then close again. And then we can look at the map estimate for our sigma. And we see, well, this map estimate is close to 2.0, but it's still not as good as our maximum likelihood estimate. And this is because our prior knowledge can also sometimes steer us a little bit in the wrong direction, away from the maybe best solution that we can think of. However, we will see soon that it is a good way in order to regularize ourselves in noisy data. So let us compare this again. I will bring up the mu MLE and the sigma MLE once again, and we see, well, they are quite close, but there is still something off in the map estimate for the sigma and the MLE estimate. However, we can use both to maybe get a good fit for these parameters at first. Now let's look at the posterior and the prior itself. And for this, we have to define a Gauss-Gamma distribution. There is no default distribution for this in TensorFlow probability, so we have to create our own joint distribution. And for this, we do a generator of a Gauss-Gamma or normal gamma, and it takes our 4 hyperparameters. It takes an alpha 0, it takes a beta 0, it takes a mu 0, and a tau 0. And based on this, we first have the random variable tau, which will be a random variable, so we have to yield it, and then we have to indicate it as the root node. So I will do this with this, and then we have it as our gamma distribution with the parameters alpha 0 and beta 0. Close again, and then we have our mu, which will be also a random variable, and for this we will use a normal distribution with the location according to the mu 0 and the scale. And now we have to take care because we multiply the tau 0 with the tau that we get out here, but since it is the precision and we define it in terms of the standard deviation, we have to take the inverse of the square root. So we have 1.0 divided by tf dot square root of tau times tau 0. Then close it up, and that's our generator. Then let's first create the prior distribution, and the prior will then be TensorFlow probability distributions, and it will be a joint distribution coroutine auto-batched. And then we have to bind our generator with the corresponding parameters. For this we will use a lambda function, and it does not take any arguments, and it then calls the Gauss-Gamma, and it binds it with our alpha 0, beta 0, mu 0, and tau 0. That's our prior, but we are not technically that interested in the prior. I just want to bring it up for comparison later. We are more interested in the posterior, but in order to get the posterior, we should define an alpha n, a beta n, a mu n, and a tau n. So I will bring over our derivations once again, And let's go back up here and let's do them step after step. So we have an alpha n, which will be our alpha 0 plus n divided by 2. Then we have our beta n, which will be our beta 0 plus 0.5 times tau 0 times n times, and then in brackets we have the mu 0 minus mu mle in brackets raised to the power of 2 divided by tau 0 plus n, then plus 0.5, and then we have the sum of the squared distances from the mean. And this was in essence nothing else than n times sigma squared mle times n times sigma mle raised to the power of 2. That's a beta n. Let's put it a little bit down here, and then we have the tau n, which is tau 0 plus n, and we have the mu n, which will be tau 0 times mu 0 plus n times mu mle in brackets, closing brackets, and then divide by the denominator, which is tau 0 plus n. And with this we have found our mu n, and then finally we can define the posterior. And for the posterior we do the same thing: distributions, joint distribution, coroutine, autobatched. We use a lambda to bind our parameters, and then we call our Gauss-Gamma generator, and we plug in first, of course, the alpha n, then the beta n, then the mu n, and a tau n, close, close, and then we have the posterior. And the prior and the posterior are our distributions here. Of course, we could have given them names and would probably be a little more intuitive, but we have a struct output with a first variable, which is the tau, and the second variable, which is the mu. And for instance, if we were to sample the prior, let's say for instance 10 times, then we would get out a result which corresponds to first a guess from the tau, and then with a guess from the mu, which is our prior knowledge on the parameters on tau. And we can do the same thing for the posterior and sample it, for instance, 10 times. And even by the things that we just looked at, you might be able to identify that our tau is now more centered around this 0.25, which we also identified to be which was the true tau, but which is also close to our map and MLE estimate for the tau. And for the mu, we are also getting more around 5. I hope this is visible, because this is like how the data that we observed morphed our prior knowledge into our posterior knowledge. And of course, theoretically, we could also check the mode of the posterior, but if I do so, then it will raise a not implemented error. And this is because in general, you can't find the mode for these joint distributions. So TensorFlow probability doesn't do this, but we found it analytically. So you have to trust me that the map that we derived is actually the mode of the posterior. But still, then there is the open question left, what the map is actually for, if it was actually a worse estimate than the MLE. And for this, we will consider a corrupt dataset. So I will use a dataset corrupt. And for this, I will copy the original dataset into the NumPy world. And in order to make it corrupt, I will augment the last 50 entries and add an 1.5 to it. So whatever you were observing, for instance, measurements, the last 50 were wrong because you had some wrong measurement tools or whatever kind of reasons you could think of. And we can also look at this dataset, and then we see that the lasts are, for instance, like 10, where we have a mu of 5 and a standard deviation of 2. And for this dataset, we can also now define a map and an MLE estimate. So let's do a mu MLE, which was the reduced mean on the dataset, and I will now do it on the corrupt dataset. And then I will also call it the corrupt MLE. And the same for the sigma MLE. So here we'll also use corrupt, and then correspondingly I also have to use corrupt here. And then we get the sigma MLE corrupt. Let's look at the mu MLE corrupt and the sigma MLE corrupt. And we see they are way off. For instance, here we have a 5.5 for the mu MLE, so it's further away from the 5.0. And the 2.2 is also further away from the 2, which we had before in our original MLE, which was just working on perfect data. So now let's define the map also. And here I will use the following formula. I will also use the corrupt data set, and I will also call this the corrupt mu. And if we then look at this quantity, well, it's also a bad estimate in this sense, but I hope I can get the point across to you. I mean, we didn't have too much prior knowledge on this, but here we are having a better estimate than the MLE. And if you recall, in the first attempt, our map was worse than the MLE, so it was further away from the original data. But here we are getting closer to it. I mean, even if it is only in the third digit after the comma. But the main point is, if you were to have higher prior knowledge, or if your dataset was even more corrupt, then your map estimate is of really good use here. And the same can be seen in the sigma map. So let's open this one up. And now we also have to use the corrupt correspondent values here. So let me put them in. I hope I matched them. Yeah, I think that's all. Then let's look at the corrupt here. And let's take a look at the sigma map corrupt. And in our MLE, we are at 2.21. And at the map corrupt, we are in 2.14. And I hope this put the corresponding emphasis on why we use these map estimates in order to regularize our estimates from the data, because in real life, data is not perfect, although we worked here with artificial data. Then thanks for watching this long video. It was really technical. I hope it was insightful into understanding these posteriors and map estimates. If there's any question regarding the derivation or TensorFlow probability or whatever, please write a comment. I would be happy to answer it. And also, if you enjoyed the video, then I would really appreciate if you like and subscribe. There is more awesome content coming soon. Here you will now see similar videos, and I hope to see you next time.